All right, now we got the good rule, the power rule. So before we use the power rule, we need to derive the power rule. And I'm not sure I've ever done that. So let's try to do it right now for the first time. So what is the power rule used for? It's used. Wait, hang on. Let me add a new piece of paper here. Okay, so it's used for functions where we have x to some power. So let's do here x to the n. N can actually be any integer, or at least it should be. It can be. So let's write that. N, not any integer. N is any real number. That's what I meant. N can be any real number. Except 0. But it works for any other one except for 0. Okay. So what can we do then? What is the limit definition of the derivative? The limit as h approaches 0 of f of x plus h minus f of x over h. Okay. So I see how this works if it's an integer. I don't see how this is going to necessarily prove it for other stuff. But let's see. So we have x plus h to the n minus x to the n over h. And make sure that looks like an h and not an n. Okay. So how does this work out? What they do is Pascal's triangle, but Pascal's triangle ideas assume integers. So I guess we'll at least for now show it that if n is an integer, it works, and then we'll look at what they did. So what can we do now? Let's copy down our limit. Limit as h approaches 0. So we can use Pascal triangles ideas where we foil this out. It's going to be x to the n plus some number. I'm just going to call it like a naught times x to the n minus 1. Actually, we know what this number is, right? Because in Pascal's triangle, like you think when it's cubed, that first number is 3. Like we know the first number. The first number is actually just whatever power that was. So that's just going to be an n. And then the other numbers, I think we're not really sure what they are. So that'll just be like different a values. Oh, but then, shoot, this has to have an h on it. This has to have an h on it. Because that's h to the 1. And then the next one is x to the n minus 2, h to the 2. And then the next one is like some other number that we don't know. But then x to the n minus 3, h to the 3. And then like dot, dot, dot. All the way down to h to the n. Alright, so see how that's just like Pascal triangle ideas? Just like to infinity. Because we don't know what n is. But then minus x to the n over h. And then let's actually get this back off the wall because we're doing the limit as h approaches 0. All right, so what can we do now? Now we're in the simplifying stage. So let's cross out our x to the n's. And then look how now everything has an h in it. So we can cancel out this h with everything on the top that has an h in it. So all of these h powers decrease by 1. But then what happens next? We're plugging in h equals 0. So when we plug in h equals 0, we get all of these things that still have an h in it, like that one and all of these over here. They're just going to go away because if h equals 0, they're just going to turn into 0. And see, all we have left is the thing that didn't have an h in it, the n times x to the n minus 1. And so that shows us that if that is our function, the derivative is what we just had down there, n times x to the n minus 1. And that is the power rule. I suppose we just showed it when n is integers, but it should work for everything as well. So that's a nice little proof. Let's see if that kind of agrees with what they did. See, they did see if n is a positive integer as well. So this proves the case where n is a positive integer greater than 1. Oh, yeah. You will prove the case for n equals 1. Yeah, that's just a constant rule. All right, so they just actually leave it there. They don't talk about that yet. All right, so we're on the same page as them. I guess we'll prove that when we need it. But there's the power rule, nicely written out how they like to write it out.